Thank you very much, Denis, for the organization of this very exciting seminar. It's a little bit out of the usual question that we ask in the lab, but I'm very curious about those kind of questions. So I'm very happy to be part of the day, and I'm very much looking forward to it. So today I would like to tell you about this particular phenomenon, inverse blebs in an inverse cyst, and I will tell you a little bit about it. So in the lab we're interested in the early development of mammals. And so this is a mouse embryo here at the zygote stage, and so during the first few days of mammalian development, we have this unique opportunity to study live mammalian development. You can grow a mouse embryo under a microscope during the first 4 or 5 days until the embryo forms a specific structure, which is called the blastocyst, which you will see at the end of this movie. This is a development which is fairly slow. It takes days to shape this particular structure, and this forces us to ask questions slightly differently from as compared to other labs who are looking at fast-developing organisms. So the blastocyst, which is the structure which is here, is composed of 2 tissues. One is called the trophectoderm in orange. This is forming an envelope around the rest of the embryo, which is composed of a fluid-filled lumen called the blastocyst in green, and a cluster of pluripotent stem cells called the inner cell mass here in blue. The inner cell mass will give rise to all of the cells of the mammalian body, while the trophectoderm, its job is to inflate this lumen, to attach to the uterus, and then to contribute to tissues of the placenta. And so in the lab, we're interested in the shaping of this embryo, and I like to break this down into 3 steps. The first one is called compaction, where you see that cells are initially loosely attached to one another, and then they form a compact mass. The second step is the formation of inner cells completely surrounded by the neighbors, and outer cells which are still in contact with the outside medium. This step is obviously very important for initiating the differentiation of the inner cells into the inner cell mass fate and the outer cells into the trophectoderm fate. And then the final step is the formation of a fluid-filled lumen, here in green, which physically separates some of the inner cells from some of the outer cells, and this lumen also breaks the radial symmetry of the embryo, forming an axis where we have the inner cell mass on one pole of the embryo and the lumen on the other pole of the embryo. And this first axis of symmetry is very important for the mammalian embryo, as it will define the point of attachment of the embryo to the uterus, and later on will align the dorsoventral axis of the mammalian embryo. And so all of this is happening all this morphogenesis is happening within 2 days. So it's a long time for changing shape. And each of those 3 morphogenetic movements takes about 10 hours. So 10 hours for compaction, 10 hours for the positioning of cells on the inside of the embryo, and then 10 hours for the formation of the lumen. And those phenomena are regulated by forces that the cells are able to generate, and those forces are primarily generated by the actin cytoskeleton. And as some of you might know, the actin cytoskeleton is turning over on a timescale of minutes. So it's a fast acting process which needs to be regulated over a long timescale. And the integration of the 2 timescales is something that we don't really understand. And today I would like to tell you about one such example of fast acting processes in the context of a slow, long-term morphogenesis. And this will be about the formation of the lumen. The lumen is forming in the 32-cell stage embryo, and you can see the lumen forming on the top left here. And I hope you can appreciate how this is a pure example of how mechanical constraints are going to be playing an important role here. There's a lot of mechanical challenges which are brought by the formation of this lumen. Some cells need to detach from one another, but you don't want the cells of the inner cell mass to separate from one another. You want them to stay cohesive. You don't want the contact of the surface cells to break either. You really want specific contacts between trophectoderm and inner cell mass cells to break, those specific contacts. You also need those cells here at the surface to stretch. And this is also another mechanical challenge which is important. And as you can see, sometimes some of those mechanical challenges can be very challenging with this cell here, which really doesn't want to let go. And so this is really the interest of the lab, trying to understand the mechanical processes which regulate the shaping of the embryo. The formation of a lumen is something which has been studied for decades in vitro, specifically using kidney cells, but other systems have been used as well, including in vivo systems. And the gist of it is that to form a lumen, what you need is an epithelium, which is polarized. It has an apical interface, a basolateral interface, and you need then 3 different ingredients for the lumen to form. You need a tight space, and this is ensured by tight junctions here in green. They just make sure that whatever you put into the lumen does not get out. Then you need polarized transport, and that is the big arrow here. And so you need transport from one interface, for example, the basolateral interface, into the apical interface. And what the epithelial cells are transporting are osmolytes. That's mostly sodium ions. What will happen then is that this will create an osmotic gradient between one compartment, here's the apical compartment, and the basolateral compartment, which will drag water into the more concentrated compartment. And then the last thing you need to do is you need to separate this interface here. You have a contact between cells, and you need to open it up. And in the case of an apical lumen, the apical interface here in red is molecularly defined, and it has no adhesion molecules. All the adhesion molecules are localized on the lateral and basal sides of the epithelium. So it is an interface which is easy to separate because it's not adhesive. The Blastocyst, the mammalian pre-mutation embryo, is a so-called inverse cyst. It has the inverse polarity. The lumen forms on the basolateral side of the embryo. The whole machinery is exactly the same, it's just that the pumping direction is opposite. It goes from the apical to the basolateral side. This is something which can happen in all kinds of epithelia, including your kidney. Your kidney are pumping both ways. Water in, water out, doesn't matter. The machinery is exactly the same. The one key difference is that to separate the interface that will form the lumen, you need to fight against adhesion molecules. And so this was the subject of a previous study of the lab, which I will briefly go through. What we saw is that when the epithelium starts pumping, water accumulates between cells, and the pressure of the fluid is fracturing the cell-cell contact. It forms multiple small water pockets, which are confined between cells, and then those water pockets, they exchange fluid at a distance and coarsen into a single entity which defines the lumen. This is how it looks like. Here is a 32-cell stage embryo, and you will see at the 2-hour mark or so that some of the contact will open up and form little blisters. There we go. You see small pockets of fluid which appear throughout the embryo, everywhere, every interface, including between cells of the inner cell mass. And then one large lumen wins over and inflates and becomes a dominant lumen, and the other smaller ones progressively disappear. And there you have your blastocyst with a determined lumen. Those small fluid pockets, they appear throughout the embryo, and they are of distinct sizes, and we could distinguish 2 kinds of those water pockets, or microlumens. We have the red ones here, which are strictly confined between 2 cells, like this guys and this guys, and then we have the blue ones here, which are confined between multiple cells. So here, if you look at a cross-section on a confocal microscope, you will see 3 cells which confine this microlumen here, but in 3 dimensions, there are more cells which are in contact with this microlumen. The microlumens which are bicellular, multicellular, they are behaving similarly. They first grow and then shrink, but the bicellular microlumens tend to shrink before the larger multicellular microlumen. They also, the bicellular microlumens also swell and shrink slower than the multicellular microlumen. So we have 2 types of behavior, and what we will see then is that one of those water pockets will inflate much larger and much faster than the others, and will become the lumen. And it consistently forms at a multicellular microlumen position. We could engineer the mechanical property of the embryo, and what we could see is that if you tune adhesion and make one side of the embryo less adhesive, the fluid will follow the path of least resistance, and it will break open those contacts faster and easier, and will guide the fluid into one position, thereby positioning the first axis of symmetry of the embryo. If you also manipulate the tensile properties of the cells and make one side of the embryo, which is less tense than the rest of the embryo, the fluid is able to push easier into the softer part of the embryo and will come in this location, again, positioning the first axis of symmetry of the embryo. And so what we could see is that physical properties of the tissue are sufficient to direct the position of the fluid. And so what we conclude is that fluid accumulation causes this hydraulic fracturing of the cell-cell contact, and this is followed by an active process of the cells pushing on the fluid to coarsen this network of water pockets to ensure that a single lumen forms. And this is happening on a time scale of about 10 hours, right? So 3 hours or so for the fracking part and 3 hours for the coarsening phase. I know 3 plus 3 is not 10, but just to get a rough idea of the time scales. But this is a very mesoscopic description of the phenomenon at the tissue scale and also at the temporal scale. And so now what we want to understand is how do those cells regulate this process at the cellular level, and the time scale of the cell is not the hour, it's the seconds. And so what we started doing was to just crank up the speed of the microscope, and you will see now one of the latest movies, not one of the first movies, but I think it's the best way to illustrate what happens. So this is a lattice light sheet microscopy movie, and so this allows us to go very, very fast in 3 dimensions, and we are looking at actin in green and membrane in magenta. And what you see is that we are imaging every 5 or 6 seconds or so, and you see those spherical structures which pop up and disappear in the green channel. So these are actin-labeled structures which are very transient and which are spherical. If you now look at a cross-section of such movie, this is now taken with a spin disk microscope, this is what you see. You see that those spherical structures, they are growing inside cells. These are spherical, transient actin protrusion which grow inside cells. If you look at many of those spherical protrusion, this is what you see with the actin channel and with the myosin channel. Myosin, non-muscle myosin 2 is a myosin motor which binds to actin and contracts the actin network. And what you see here is that the membrane inflates naked, without actin, without myosin. And then when the protrusion is retracting, that is when there is actin and myosin. You can quantify this behavior. The graph is a bit complicated. I will guide you through. You have 4 curves, unfortunately. So let's look at the gray one for now. So the gray curve is showing you the size of the protrusion, which grows within 10 seconds. It's a very fast growth. And then it shrinks within 40 seconds. That is a gray curve here. At the same time as the protrusion is inflating and deflating, the membrane is getting down by a factor 2 and then back up by a factor 2, as if the 2 membranes will separate and come back together. And then what we see for actin and myosin in green and red is that actin is coming up first, but after the protrusion has grown, and myosin is coming a little bit later, and then it accumulates and it fades away after the retraction. Those dynamics, about 1 minute time scale, growth without actin, shrinkage with actomycin, it's a typical dynamic of a bleb. You might all have heard about blebs in the context of apoptosis, in the context of cell migration, or cytokinesis, and these are blebs. But the main difference is that those blebs do not grow outward, they grow inside the cell. To visualize this, what we can see is we can label the fluid, which is trapped between the cells, and here the fluid is labeled in blue. And what you see are fluid pockets, like this very large microlumen here, which has a little bit of blue inside, or a small one here. And sometimes you see those transient structures which fill up, with the fluid. And so this is one such inverse blebs. Within a few seconds, it inflates, it fills up with the fluid, and then it retracts and pushes back the fluid into the system. And so what we see is that we now have not one type of fluid pocket, we have 2 types of fluid pockets. We have the ones which are the stable microlumens, which stay stable on a timescale of hours, and we have those very short, transient inverse blebs, which grow and shrink and share the same fluid. So to try to understand how those 2 types of water pockets would coexist at different timescales, we did a different kind of imaging, where we image the embryo now every minute. This is enough time to see the flashes of the inverse blebs. You see there's hundreds of them. And we can also detect the formation of those microlumens. The movie now is a bit small here. You might not be able to spot them. But believe me, we can actually spot them on this kind of movie. And so the goal of this was simply to see which one appears first. And so what we see is that consistently, the microlumens, the water pockets which are stable, appear first, systematically. And then within 20 minutes or so, this is when we start to see the inverse blebs popping up and down. This lasts for 3 hours, so 3 hours of intense blabbing activity. Then those blabs disappear, the microlumens still persist for another hour or so, and then we have no more inverse blabs, no more microlumens. But what we see is that there's this inverse blab phase which is contained between this microlumen phase. The inverse blabs always coexist with the microlumen. We wanted to get a better idea of this dynamics, and so we started doing yet a different kind of imaging. Again, the challenge with multiple processes happening at different timescales is that you need to adapt your imaging strategy so that you can capture all of those timescales. And so here what we did is one movie every hour of the full volume of the embryo. So we have the full stacks of this maximum projection. And so this is imaged every 10 seconds. And you might be able to see that there are those flashes here. And now we can count every single blab events within the entire embryo. And what we see is that there is a peak blabbing activity with about 15 blabs per minute in the entire embryo. And the entire blabbing phase is lasting about 3 hours, as I mentioned before. But there's an increase in blabbing activity and then fading away. And then we also measured the size of the lumen. And what we see is that when the lumen reaches a critical size, which is about the size of a cell, about 20 picoliters, most of the blabs have already occurred. So most of the blabbing is happening before the lumen is properly formed, properly coarsened. So the coarsening is happening as this blabbing activity is happening. So what we see are those inverse blabs which form during the coarsening of the lumen. So we have this long coarsening phase where all the fluid is gathered into one single place, and this is associated with an intense blabbing activity. Blabs which are inverse, which grow inward. And so the next question we wanted to ask is what controls those blabs? And what controls the formation of an outward blab is a difference in pressure between the medium and the cytoplasm. This is also true for inverse blabs. Inverse blabs have also been observed in other contexts before the mouse embryo. This is the first description of an inverse blab. This is a blood vessel in a zebrafish embryo. And in the zebrafish embryo, the heart is pumping the blood, and it pushes at the tip of the blood vessels which are forming. And what you can see is that this endothelial cell here has blebs which are entering into the cell, and then the cell is trying to push back those blebs. It obviously fails because the heart is such a strong pump, but initially it tries to push back and retract those inverse blebs which grow inside the cell. If you stop the heart pumping, then this blabbing activity is stopping. There are other cases where we think that inverse blebs are observed, but they were not described as such. Here, this is a system where they have taken kidney cells in a pressure device, and they could artificially raise the pressure from 0 to 200 Pascal. And 200 Pascal, to give you an idea, is about 1/10 of the pressure of the lumen of the mouse embryo. So it's a relatively low pressure compared to the pressure that we have in our system. And what we see here is that when you raise the pressure above a certain level, you see spherical actin protrusion with dynamic which are compatible with inverse blebs. So we think that pressure of the external fluid confined between the cells might be important for generating those inverse blebs. So what we did is simply to tune the pressure that we have in our system. And so here what we have is an embryo which is undergoing blabbing. And here we have placed the same embryo into a drug which prevents the osmotic transport. So there's no more osmotic transport of sodium. The fluid is not accumulating any longer. And within 50 minutes, what we see is that the blabbing activity stops. It doesn't mean that, so as you can see, there's still fluid. The fluid is not gone. What we think is that there's no more fluid accumulation, and therefore the pressure is not raising anymore. And so we think that you need this pressure constantly to create those inverse blebs, just like in the heart, just like in the kidney cells. The main difference that we have in the context of those inverse blebs and the one that I described before is that now the inverse blebs here, they do not happen at a free interface, like in the endothelial cells. They happen at a cell-cell contact. And so we think adhesion, okay, this is a quantification of what I just mentioned. We think the fact that it happened at contact is very important. We have adhesion molecules, which are initially homogeneously localized along the cell-cell contact. And here, after the fracturing of the cell-cell contact, we have those water pockets. And the pockets are cornered by adhesion foci. This is a 2D slice through the contact, but what you have to imagine is a capsule, which is surrounded by a circle of adhesion molecules. And what we suspected is that those adhesion molecules would act as a confiner. They would confine the fluid, prevent it from going as free as it would like to away from the cell-cell contact, and that might help raising the pressure. So to test this idea, what we did is reduce the adhesion, reduce the confinement, and see if that would be associated with a reduction of blebbing activity. And so this is a wild-type embryo, and this is a heterozygous knockout for E-cadherin, which is the main adhesion molecule in this system. It still has the paternal allele of E-cadherin, so it is able to make it, but it has just less adhesion. And so here what you see is that this embryo, which has less adhesion, is going to form a lumen extremely fast, actually twice as fast as a wild-type embryo. And that is because the fluid is able to break the contact much easier, much quicker. And what you might have been able to see as well is that in those embryos which have little adhesion, they form a lumen without inverse blebs. Only a third of the embryo which are knocked out for ECAD, which are heterozygous knockout for ECAD, only a third of those embryos form inverse blebs. And when they do form inverse blebs, there are much fewer than in a wild-type context. So they very rarely form inverse blebs, and we think that you need this adhesion confinement for the formation of those inverse blebs. And so this is our general hypothesis, and we discussed this with Argo Mukherjee, who is a theoretical physicist who could formalize all of this. And so we have now this model of the formation of fluid pockets. And so here we have fluid which is confined between adhesive sites, here, which are in orange. And the size of this water pocket is going to be regulated by how much pressure in the fluid you have, how much confinement you have provided by adhesion, and also how much tension you had at the surface of the cell. And if you play with adhesion, what you see is that, and that is coming out naturally from the model, is that you have the breaking of you jump over a potential barrier, and this provides a critical size or a defined size for those water pockets. And this is something that we had noticed. The blebs have a characteristic size, the water pockets have a characteristic size. We didn't have an explanation, but the explanation for this characteristic size comes naturally out of the introduction of a confiner provided by adhesion. So if you do not have adhesion, then the water pocket will grow indefinitely. There is no stopping, and that is what we think is happening in the embryo without as much adhesion. It just inflates without stopping until something else stops it, which is the epithelium above. Same thing happens for pressure. If you increase the pressure, that is when you will be able to inflate those water pockets. Again, if you have no confinement, you will just increase their size indefinitely. The blebs do not grow indefinitely. Something stops them eventually. And what stops them is this appearance of actin and myosin. Just like for regular bleb, blebs are retracted by actomyosin. And so if you look at actomyosin in this wild-type embryo, it is accumulated at the bleb, and then when it appears at the bleb, this spherical structure is retracted within 30-40 seconds. And we decided to knock out the different paralogs of the non-muscle myosin 2, and that is this guy and this guy, 2A and 2B, or 9 and 10, call them however you want. This is a non-muscle myosin 2A or myosin MYH9 heterozygous mutant, and those guys, they do bleb, but the blebs take longer to retract, and this is not the case for this particular myosin paralog. Interestingly, if you look at outward bleb, it's the same. The myosin paralog, which retracts blebs, is this guy, not this guy. You can also treat the embryos with blebistatin, which is a drug which inhibits myosin. You see the same effect. The DMSO control take about 40 seconds to retract. The blebistatin treated ones take a bit longer. We also occasionally see, but this is very sporadic, we don't have a way to control, we also sometimes see those kind of objects inside the cells, which might be blebs which did not retract properly. So you might want to have this retraction happening, otherwise something bad might happen. And so this is now to complete the model. We discuss the presence of adhesion, which confined the fluid, that is the orange parameter. We discuss the increase in pressure, and now we just added a tension at the surface of the cell, which is provided by this acute accumulation of actomyosin. And this is what prevents the uncontrolled growth of the inverse blebs. What the increase in tension will do is that it will bring back this energy potential to a higher level and force a retraction of the inverse blebs. And so we form this loop of extension, actomyosin recruitment, retraction, which looks very much like what we see qualitatively in the experiments, where the bleb is increasing, actomyosin is recruited, and then the bleb is retracted and actomizing is fading away as well. So we just have a good agreement between the theoretical modeling that Argo developed and the formation and retraction of inverse blebs. So to conclude, we think that those inverse blebs, they grow due to a global increase in pressure, that is the accumulation of fluid, but then we have this local confiner, which is also important, and then they're retracted by actomizing. And so we think now we understand a bit better how those protrusions are growing and retracting, but what do they do? What are they good for? So this is where it gets a bit trickier, but we have a good idea. So obviously, if you do not retract those blebs, something bad will happen. You will have this protrusion inside your cytoplasm that is not something that the cell may want, right? But beyond this, what do those blebs do? So if you look at the blebs, they basically grow a bit everywhere, and they inflate with fluid, and then they flush it away. Inflate with fluid, flush it away. And they do it again and again and again. And they basically just mix the fluid within the cytoplasm, within the entire embryo. And if there's no specific localization of those blebs, then this is a futile phenomenon. It will just move the fluid around without any direction. But what we notice is that not all interfaces grow inverse blebs. We have those multicellular microlumens at the edges of the cell-cell contact, and then we have the cell-cell contact, which has bicellular microlumens. Some of them cannot be resolved with high-resolution microscopy. We can imagine that there are some here. And what we see is that the inverse blebs do not form at multicellular microlumens. And you can see it on this entire embryo. All the blebs you see, they form at bicellular microlumens. And that means that we have some fluid pockets which are able to grow blebs and deflate the bleb, putting back the fluid into the system. And then we have those guys on the edges which are not able to push back the fluid. And effectively, this is transforming them into sinks, which will just absorb all of the fluid that is flushed away by those interfaces. So the job of the bleb might be to just get the fluid away from cell-cell contact, push it to the side. And then we have those sinks. And so then we decided to test this hypothesis to play with the topology of the embryo. In the embryo, we have 32 cells, which have between 10 to 20 of those multicellular microlumen, which gives them 10 to 20 of those hydraulic sinks. And we can play with the cell number, and so we can dissociate the embryo to form quartets of embryo at the 32 cell stage. And those guys will have, depending on their configuration, 1 or 2 of those multicellular microlumen. We can also have a doublet of cell at the 32 cell stage, and those guys will have no multicellular microlumen. They will only have bicellular microlumens. When we look at those quartets and doublets, this is what we see. We have quartets with 2 multicellular microlumens, one here and one here. You will see that they will start to form microlumens everywhere. They will start to form blebs. And then a lumen will appear somewhere below, and the blebs are stopped, and this is done. So it's a quick process because it's a small system. You don't have so many microlumens to deal with. And then in the meantime, you have this guy here. It has a very small interface, but you see it's still going at it. It has a string of bicellular microlumens, and it seems to be struggling for quite a while to finally gather all of the fluid into one location. And so here we have 2 sinks which compete with one another. That is much fewer than 10 to 20 sinks to compete, that need to compete. And the blebs are able to effectively flush the fluid away into those 2 sinks. Here we have no sink. We only have microlumens which have the same properties, the same ability to flush the fluid away. And so they keep on blebbing for hours and hours in a futile cycle that just pushes the fluid from one bleb to the next, to the next, to the next. And it's not efficient. And so despite the fact that those guys are much smaller, that they would, in principle, you would expect them to go faster, they don't. This is a whole embryo. It takes 5 hours for the entire microlumen network on average to coarsen. The quartets are much faster because the system is simpler. This is not happening for the doublet. The doublet is not faster despite its smaller size. And so we think this is compatible with the idea that those inverse blebs are operating as hydraulic pumps that just basically just pump the fluid into the system, and their specific, their topological specificity allows them to promote the coarsening of this microlumen network. And this is now on bioRxiv since a few months, and this is done by Markus Schlifka, who defended his PhD last week. He's on the job market. He's very good. Poach him. We are also hiring, and I would like to do also, and this is also done together with Argo Mukherjee, who is at the ENS, who did all of the theory. I would like to make one last announcement. We are looking for a new group leader in the department. Please check it out if you're interested. Please recommend it to people who you think might be interested. We're in Paris right now. You know that it can be a very enjoyable city. We are located here. This is a red dot, and those green and yellow dots are restaurants that I like. So, thank you very much.